So anyway, I'm going to talk about actions as data, and this is the goal of this talk is actually to explore a bit, given that we are in an advanced conference, how to use functions within your types to describe behaviors, to describe, well, we'll see what I mean by behavior. So I will essentially shortly recap a few things about data classes that we need to use. And then I will just go and talk about how we describe this action with functions, and then we will go into doing fancy stuff with this, and at the end we will kind of come to a pattern, the actions as data pattern, or whatever you want to call it. So yeah, I like to use this as an example. So yeah, my son and I play this too much. That's too much money. But anyway, there is this game. If you ever played one of these geeky games where you have a card and the card has a tags, and then you try to knock out your opponent Pokemon and blah, 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 blah. You don't really need to know much about this, only that our goal is to model these cards in Kotlin. So we are going to try to figure out if we were to create software for a game like this, how would you model, what will be the types you create, the classes you create to model one such card. So if you just start looking at this, you have the easy things like a name, and then you have types like this lighting thing, which is something in the games. You have different types of Pokemon, like lighting and fire and wherever, and you have some health points, that's in the corner, that's 80, and you have some attacks. And actually, this is the only thing we will care about this. So there is a bunch of extra stuff all around. We don't really care. This is actually going to be enough for this. So the nice thing is that you can very straightforward translate this into, for example, a data class. You can just go and say, well, my card has a name, a type, some health points, an attack, and then you just go and say, well, my name is a string, and my type is going to be some kind of energy, and then an integer for the health points, and the list of attacks. So far, hopefully so good. That's mostly to, that we all get into the syntax and all of that. And then there is also something about the energies. There are like 10 types, some regular ones, one which is like a star, which counts for everything. So like if you have this on the card, that means you need 2 lighting and 1 of any other to attack. Doesn't really matter a lot. The main thing is that this allows me to also remind you about enumeration classes. So this is a typical example of an enumeration, right? You have all these things, colorless, grass, fire, water, and this is going to be our energy type. So which, if you remember, we use this in the Pokemon card class. And then we're going to start by trying to model this simple attack. And by simple, I mean, and you will shortly see why there are more complex ones. This has a name, again, like Electro Ball, some cost, which is also some energies, and then it does some damage, which is 60, right? So hopefully, so far, so good. Because I really want you to do things, I thought, why don't you get out your laptops and try to write the code for these things? I actually put this on internet, so you don't have to open IntelliJ or anything like that. You want to do it? I can. Otherwise, we will dance more. Your choice. I'm an even better Latin dance trainer than I'm a Zumba trainer. So, just. By the way, I know you can do that. This is mostly so you take up your laptop, because later I will actually ask you a harder question. And I don't want then everybody to open their laptops. Because that's like at the end when she will tell me I only have 5 minutes left, so I don't want then everybody opening the laptop and me like, no, you're opening IntelliJ, it's going to take 4 minutes out of my 5 minutes. No. Okay, it works. All our internet works, right? That's checked. You see, what's the Wi-Fi password? I should have asked about the Wi-Fi. Anyway, yeah, somebody's coming and trying to figure out why there are Pokemon on the screen. We are modeling this thing. So Ah. Cool, so I know you can do that, right? This is like, you can easily translate this thing into the right correspondence of constructors and so on. So, yeah, just continuing to model these things. If you keep playing the game, you will actually learn that there are different kinds of cards. You have like the monster cards, but also the energies and the trainer cards, which do have interesting effects. And if you were to model this, actually there is also something you can do in Kotlin. And this is actually a pattern I really like to use in my code, which is, you create your kind of sealed interface, and then there are several classes with implement the interface. So these are like the 3 kinds of cards. And because the interface is sealed, that means that there are no more possibilities. So this is actually like modeling the domain you want. So this is like the basics of what I want to use for the talk, right? So the idea that if you want to model data in this kind of functional-esque style, what you do is you create sealed interfaces and enumerations to represent choice or sums or whatever you want to do it. That's what we did for like the type of energies and for the type of cards. And then you have several data classes representing the actual sequences of values. Like in the case of a trainer card, we had the name and the text. In the case of a Pokemon card, we had all the attacks and all of that. So that's like where I'm counting on. And by the way, people know this as algebraic data types, if you ever hear about this. So there are other languages, and they all happen to call them in different ways. Doesn't really matter. What matters is that it's early, and I've already lied to you, because this was a simplification of the domain. I said, oh, the attack just has 1 damage that you can do. But actually, if you open these cards, they actually look more like this. Things like, oh, flip a coin until you get tails, and then this attack does 30 times the amount of heads you get, or draw 2 cards, or whatever. So the question, so what you see there is, if you try to model this domain at some point, you figure out that there are more actions than this damage. You can draw cards, you can discard cards, and actually this action may depend on some state. Like, for example, draw a card. You can imagine you have a deck of cards. So if you are implementing this thing, that means depending on the state of the game, if you have cards or not, you maybe can draw or not. Some also depends on random events, like flipping a coin. So you flip a coin, and depending on this, you do something else. And this also brings things like conditionals, right? Because it says, if you get a tail, then do this. If you hit heads, do this. So the question is, how do we model these actions? How do we represent, not how we execute? I mean, I know that you can all write something which will do the random thing. The question is, how do we model, how do we describe as data the fact that, for example, you have something to do when you have tails and something to do when you have heads? And that's the actual goal of this talk. Try to think about how you do this. So what we are going to do is actually first we are going to just replace this damage we had with an action that is going to be a different type. And I will actually make damage one of those actions. So I will bring this pattern I was introducing before, where I have my sealed interface, which is action, and that will represent all the primitive actions we can do in the game, like flipping a coin, do damage, draw a card, things like this. And damage is just going to be one of the actions. So if you have something like this, like coin flip, where you now have a new primitive action. Do I have like a laser pointer? Yeah, doesn't matter. If you have a new primitive action like flipping a coin, what we are going to do is we are going to model this as a new data class extending this action. So this flip a coin now is a new type of action. That's what the extends is saying here. And here what we are going to do is to model the 2 possible branches. Because remember, we are not executing something, we want to model this. We want to be able to describe. And if we are describing this card, we need to say what happens when heads come, what happens when tails come. And we are going to do this by, well, let's start by just having two different fields, one that says what happens when things are heads, what happens when things are tails. So this attack would actually be modeled in this way. This surprise attack is an action, and then we have a flip coin constructor because the beginning of the card says flip a coin, and then if it well, essentially it says if it tails, it does nothing. So if tails, it has 0 damage. If it heads, it has 30 damage. And apart from kind of looking at how one particular example looks here, what I would also like you to notice is that damage works kind of as a terminal action. It's always the end of the sequence. You will always have flip a coin, which has another action in the fields. And that means that if now you have flip a coin, then you have to, again, give me more action. So you always end up with damage in one point or another. That's going to be the final action. And that's going to actually be an important part of the whole generic pattern. Right. If you keep doing this, you can actually, well, start nesting things, for examples, and say, well, we had this surprise attack. Let's invent a new one, which is double surprise, which says, flip 2 coins. If both are heads, you do 50. Otherwise, you do 0. How would you model this? Well, now you have to flip a coin, right? If it's tails, you know why keep trying, because you already had a tail, so you get the 0. That's going to be this case here. Otherwise, you flip another coin. That's going to be there. You get the heads, and then you have 2 possible outcomes, right? You can have another heads, and then you have 50, and then you can have tails, and then you have 0. So you can see that by actually combining these pieces, and by the fact that our flip coin doesn't directly return the damage, but actually calls action again, we can build bigger and bigger action with these building blocks. Cool. So just to bring a few words, because it's early in the morning, and that's the point where you will actually absorb some knowledge. Who knows what you will be able to get from the 4-hour talk? Well, when people talk about this, especially in like functional programming communities, they actually say that action is what you call the syntax of your language. It's all the algebra. That's essentially kind of defining what you can say in the language. And in our case, the language is what we can do with the actions in our car, what the attacks can say. The other side of the coin is what we call an interpretation, and that defines how this actual thing is executed. So if you take this description, eventually you will like to execute it in the game. You will actually want to perform the coin flip, for example, with a random generator. And that's what people call interpretations or semantics or things like this. And the nice thing is you can have one single language, but you can have several interpretations. It's like, we have the word cow, but it can refer to like a cow some kid draw in a piece of paper, or to an actual animal or whatever. So let's try to figure out what we can do with this idea. So the easiest thing we can do with our actions is just try to execute them straight away. And this will eventually return some damage, some integer. So if we are already in the damage, then we are done. That's the information. Otherwise, in the flip a coin, then we will randomly flip the coin. Well, get a Boolean, which is like flipping a coin. And then if we get true, then we keep going with the if heads branch. So we keep going with that action. If it tails, then we will go with the other branch here. So this is also part of the pattern. So when you have this kind of things which describe action, which describe behaviors, you often have this kind of functions in which you do a bit and then keep going, calling yourself recursively. And you can see that actually the function was marked as style recursive because you can then, the compiler can then optimize it and not a Stack Overflow. I don't think nobody will create something with, an action with 10 million actions inside of it, but who knows? We can just mark it tail recursive And that's also kind of part of the pattern here, that everything we get is tail recursive. So now that we have this, we can actually ask ourselves, okay, but what if I want to test this, right? Why if I want to test that the thing I've described is actually what I've done? Well, what we can do is define one of these other interpretation, and now it's actually what I want you to think about it. You can try to get something, you can try to do something similar, but now instead of actually flipping a coin, we're going to like control the future. So these outcomes are going to tell us what is the future. So what is the things we want to get in each case. And the good thing is this is great for testing, because now we can say, okay, let's check whether if we have our surprise attack and have heads, or well, like true as our outcome, we actually get the result we want. Or if we have first false, we get a 0. And of course, for that case, that's kind of stupid, because yeah, the code is so straightforward. But if you have more complicated actions, and that's what we are going to do after this, it really pays off to have this kind of purified things. And just to be clear, I'm showing this an example, but imagine if your actions are not actually something in a card game, but your actions are actually describing what you can do in your database. You know, the actions you can perform in a financial contract. Then you really want to test that things go the way they should go before actually executing them and, you know, moving money around things. I mean, if all the money gets to my account. But other than that, you really want to do this. So, yeah, I'll give you a few minutes, you know. And all relax, it's 9 in the morning. And you have questions, you can ask him, and he will get you the microphone.
Somebody got a question?
Hmm?
Not yet.
This is like something on Play Kotlin, so you can even open it in your phone. Yep. Oh, Wi-Fi password. I don't know about that.
Yeah, the Wi-Fi password. Who was asking? Je hebt deze. Dus je weer deze. I tried the third one. It doesn't seem to work. Then try the first. yeah, it's Q factory internal. I don't see it, but you either.
Yeah, I don't see it.
Yeah, I did see it in my.
Q factory worker. Maybe also you have klein en groot as well, so it all starts with three things. Q factory.
Well, let's get to more fun stuff. So, by the way, this is what I came up with. I'm not very proud of this code. If somebody knows how to not call first and drop one all the time, I will happily get a better thing. But it's just essentially we are just looking at the first thing, and then depending on this, we just do like before. We are just executing, but just the execution requires the rest of the outcomes, so we will just drop the first one. And what happens if we don't have enough? Well, yeah, okay. Just we can think about, that's for testing, so that's fine. Cool, but what happens now? I mean, you then get to this kind of things, like this iron tail, which is flip a coin until you had tails. And it's like, wow, there is like a loop in my action. Kids don't know it, because they just do the thing that the card says, right? But that's like a loop, like while flip coin, tails, do this. So we need to figure out what is the way to do this. And the first thing that may come to mind is, okay, we can just introduce yet another action, right? Some kind of action which describes looping, some kind of fancy constructor where you get, I don't know, some Boolean thing, and then another thing, and then you kind of execute this, you execute the loop there. But actually the cool thing is that once we have these primitive actions, Kotlin gives us enough power to actually describe these kind of things within the language, so we don't have to add any extra thing. And in the case of Irontail, for example, what we can do is to use a recursive worker. So essentially what we say is we are going to create a flip coin constructor, and then if it heads, then we are keep looping. So we are going to go again into the recursive loop, the worker, and we are going to accumulate some damage. So we will start with 0. So this is where we start. We start with 0. We get heads, then we go into the worker with now 0 plus 30, 30. We get heads again, then we go with 30 plus 30, 60. Now we get tails, then we are done. We have the damage. And the important thing, again, to show here is that we don't need any additional thing. We can just use Kotlin to implement this thing. Except this won't work. Can somebody see what's going to happen if I try to then call irontail.execute? Well, actually, we will get an infinite loop because, the worker never ends, and all this thing is evaluated right away. So we get the flip coin, and then it needs to evaluate both things, right? In our mind, it looks like, because we always think on this execution thing, that we are only going to go one step farther. But what actually happens is that the worker never ends, and then we get a Stack Overflow error. We can fix it by actually delaying the evaluation of these things, and that's where functions are coming into the game here. So we are going to replace, instead of having just an action, we are going to have a function with no parameters, that's okay, which returns an action. And that means, that the code doesn't change that much. We just need to add some curly braces here and there, because now the if heads and if tails actually require an action. But what happens here is that now evaluation stops there. So it gets the flip coin, and then we have a function. But we don't look inside the function until we execute this. So with this trick, which is actually a trick coming from other languages, like people call this thunks or lazy ways to lazy evaluate things and things like this, you can actually stop evaluation where you want and say, oh, okay, at this point you just flip a coin. When you give me the result of the flipping, I will tell you what to do, but not everything in one go, because I cannot do this because this is a recursive thing. So this is one other technique you can use when defining these actions. And now that you know about this, we can actually have more and more actions. You can have things like draw 2 cards, or like discard, whatever. So we just add new variants, right? So we just now add new things which implement our action interface. However, if you think about this draw two cards, you would like to have, imagine that the card doesn't just look like draw two cards. It says, draw a card. If what you draw is blue, then do this. Otherwise, do that. So you would like to have some kind of conditional thing there. And for this, you need to know what card you draw. But now you have a problem, because in the case of flip coin, you had two outcomes, right? It's head or tail. So we can model this as two fields. But in the case of cards, I don't know how many cards have been printed about this game, but they are on the thousands. We cannot have 1,000 fields. I'm pretty sure something overflows in the compiler or just is stupid, just to name it. So instead, what we are going to do is, again, using functions, we are going to define this as the next step is going to actually get the card that you get. But this actually might look a bit weird because, so again, we are trying to describe the actions, and in this description, we will eventually get to the point where we tell you, like when you execute this thing, what card you get. But in the description, you are actually taking the other side. You have to describe me what do I do when you tell me what card it is. And that's why we have a card here. And by the way, once we have this, we can actually model this in this way, because in the same way that we had before the flip coin, which heads and tails, now we can actually have a very simple enumeration for heads and tails, and then our flip coin becomes something which requires a function which, given a flip outcome, tells you what action should it be. And if you think about it, that's essentially, if you then do a when on the flip outcome, you are essentially describing what these two things are. So this actually gives you very nice syntax. I actually like when you get to this point, because your flip coin, which before looked like if heads, if tails, it looked a bit weird. Now your flip coin gets a function, and because of Kotlin's ability to drop the parentheses when you have a trailing lambda, you can just write the curly braces there, and then you say, okay, the flip coin will give me an outcome, right? So if you think about the point of view of describing this, and I match on the outcome and tell you what I do next. So you get like nice syntax for these kind of things. I actually had some more time for practice, but I only have 10 minutes left. So one thing it's nice is you can, for example, introduce this draw card and have an attack which says draw two cards, and it will look a bit like this, right? So you draw a card. You don't really care about which card you draw, so English is difficult. So you don't really care about the card. We are not just given an argument there, but we have a draw card, and then the next thing is a draw card, and then you do 0 damage, because that's, it should be 20. Never mind. So, because you are drawing two cards. So actually, the last thing I wanted you to think about, but I think I don't have time for this, is, So imagine that you want to have an action to draw n cards. So, we have an action to draw one card, and we would like to have things which says draw two cards. And again, you could think, I will just add this as another action. So instead of having a draw card with no arguments other than what to do next, I will give it a number. But we can actually have a very primitive action, which is drawing one card, and then implement the draw n cards using Kotlin code, as we have done for the recursion. So the idea here is the more primitive your action, the better, because that means when you are writing this execute or this simulate function to interpret this, you only care about the tiny actions, and then the rest is actually an scaffolding given to you by Kotlin. So the idea is that the argument in this case should be like the amount of cards to draw, and what you get back in the same way that when you draw one card, you get one card, as in the function here, you should get a list of cards. So we would like to write this function And, we can fake it is actually a primitive action by doing a capital D, because, everything that starts with a capital is a constructor, even though it isn't. So it should look a bit like this. And I want to show this again for the sake of how the pattern looks in general. All our actions have some additional information maybe, but they always end up with this very last field, which is a function, which has an argument, which is the kind of things we get by executing the action. So remember, if we flip a coin, that was the flip outcome. If we draw one card, we get a card. If we draw n cards, we get a list of cards. And then they always go back to the action. And that's how we tell what we should do next. So you can think about it. It actually looks pretty similar. It looks very big, but it's the same idea of the recursion, except that we have this amount which is decreased in every recursive thing. So I don't want to show, you can look it later, think about it. It's actually quite nice if you really want to understand the whole thing. So let's see, we have all of this now. So we have all these different classes extending action. We have flip coin, draw card, imagine we have this card. You can imagine something about shuffling the rest of your cards or something like this, which actually if you shuffle, you get no information back, but you still can do more things. So I don't know, shuffle your deck, then draw 2 cards, shuffle your deck, then draw 1 more card, then do 20 damage. These are the kind of things we can now express in our language. So the idea now is to look for patterns, because I was telling you I'm describing kind of a pattern. So I was already pointing at this, but just to make everything crystal clear, what we have here is that every action ends with what we call a continuation, which is this function which, tell us how to continue working with it, which is a function which recursively goes into action again. And then this continuation get whatever information we are consuming, the flip outcome, or nothing if no data is consumed. And then the other part is we always have a final action, which in this case was damage. And that's the way you end. You always need a terminal action. So all of this is a general pattern you can use to describe any action. You always have one single interface, which is like every possible action. You have one terminal action and then a bunch of primitive actions which always end in a continuation. If you want to do it a tiny bit more general, you can actually make this thing parameterized by like a type parameter, and then this allows you, so instead of damage, we have here done, and this allows you to return different kinds of things. So here we are always ending with a number, but you can imagine you can have different outcomes. Maybe not in this case, because again, the model is very simple, but if you go into modeling, let's say financial contracts, then you may get some money, or maybe here is an ID of a transaction, and here is a user. This allows a bit more flexibility. Anyway, that's a bit of the summary. Data with functions inside allow us to represent actions. We've seen that you can have one single data type to represent this, what we call the syntax, but actually have different functions operating on this, which are the interpretations. And the other important thing is sometimes we need to delay execution, otherwise we get a stack overflows, but this actually opens the door to using recursion, to using branching from within Kotlin, so we don't have to introduce this in our language. We don't have conditionals in our language, yet we can do conditions in our language because we have if heads, if tails. Yeah, so that was all. I actually wrote a book which has this thing, like at the end, and you can get free copies in the booth of Xebia Functional. I don't know how free they are. You need to give data or something like that. Yeah, but it's been a pleasure, right? Enjoy the rest of the talk. Enjoy the rest of the day. And if you want to talk about this cool thing, I will be in the big arrow thing, which says arrow in big letters. So there is no way you can miss that. Yeah, so hope you enjoyed it.